Okay, so this is your 5th lecture. Technically it's the 6th. But since I consider the A equals LU lecture to be a continuation of what we've done in the 5th lecture and the 4th lecture, so we're not going to consider that to be a separate lecture. Okay, so this lecture is on determinants, right? Why we need them, and what they mean physically, and so on and so forth. So remember from your first assignment, you were made to prove that the inverse of a 2 by 2 matrix is given by 1 over something, right? A11, A22 minus A12, A21 times A22, negative A12, negative A21, A11. So what you did was basically you switch these guys. You switch these guys and you give these guys minus signs. And of course, since this is in the denominator, this cannot be equal to 0. So this quantity that you have here, A11, A22 minus A12, A21, this is known as the determinant of the matrix A. Of the matrix A. Now notice that the determinant is only defined for square matrices. You're not going to find determinants for matrices, m by n matrices where m is not equal to n. Another thing, notice that we use a single var on determinant, right? For determinant. And double var are on the vector, so this means modulus. Don't confuse the two. So for example, if you have a 1 by 1 matrix with just one element, the determinant is given by single var x. This is not to be confused with a double var. Okay, so determinant is something that we will define inductively. What does this mean? This means that the determinant of a 3 by 3 matrix, for example, okay, the determinant of an n by n matrix is defined in terms of the determinant of an n by 1 by n by 1 matrix, and so on and so forth. Right, so now that we have that out of the way, now how do we calculate determinant of a matrix? Okay, so if you replace the so this is the matrix A22. This is the matrix A, and this is the matrix A, and this with the with these bars, with the vertical bars, is determinant of A. Make sure you can tell the difference. Okay, so now we're going to define a few things. Okay, so whenever you see a blue border from now on, blue border, this means definition. If A is a square matrix, then the minor entry Aij is denoted by Mij. The minor of the entry Aij is denoted by Mij, and is defined to be the submatrix that remains after the ith row is it to be the determinant of the submatrix that remains after the ith row and jth column and deleted from A. Okay, so for example, if you have a matrix that looks like this, 2 by 2, let's take a simple 2 by 2 matrix example. So minor M11 is the determinant of the submatrix that remains after you cross out the first row and the first column. So this is equal to 822, right? And the number -1 I plus j times mij is denoted by Cij, and it is called the cofactor of entry Aij. So C11 in that case is -1 times to the power of 1 plus 1 times 822, which is equal to 822. Okay, so if we start with the matrix X, 3 1 -4 2 5 6 1 4 8. So what is the minor of X11? What is M11? So you cross out the first row and you cross out the first column. What remains? 5 6 4 8, right? And the determinant of that is a M11. And the cofactor C11 is, of course, -1 to the 1 plus 1 times M11, which is 16. Similarly, the minor X23, the minor of element X23 is the is what remains after you cross out the second row and the third column. So what remains is the matrix 3 1 1 4, and you find the determinant of that. That is 12 minus 1, which is, so this is M23, which is 11. And of course the corresponding cofactor -1, 2 plus 3 times 11, which is -11. So notice that the cofactor equals either the minor itself, the corresponding minor, or the negative of the minor. Okay, so the next. Okay, so the next exercise tells you that the exercise tells you to calculate the minors Mij and the cofactor Cij of the matrix X. So you have a matrix given our matrix X. What are the minor? What is each minor and what is each cofactor? So you should do. So the exercises are in bottle green. Okay, you should do this. You should. In fact, you must do this. You have to do this. You must do this. All the exercises are important. Okay, so now if we have a determinant of A, right? So remember matrix A. So what is C11? C11, so A was of course A11, A12, A21, A22, right? So this was A. So C11 was this, C12 is this, C21 is this, and C22 is this. Now, determinant of A can be written as A11, C11 plus A12, C12. Now C11, what was C11? C11 was A22, so this is A11, A22 minus, okay, plus A12. What is C12? C12 is minus A12 minus C12. C12 should actually be A21. This should actually be A21. This is a typo. This is A21, right? So this should be minus A21. So you get A11, A22 minus A12, A21, and so on and so forth. Notice that all of these four expressions are equal. Okay, so this should be M12 is actually A21, and C21, that this should actually be equal to A11. I'll have this corrected. And C22, no, this should, okay, let's evaluate these again. C11 equals negative 1, 1 plus 1, A22, C12 equals negative 1, 1 plus 2, A21, C21, negative 1, 2 plus 1, A12, and so that's C12. No, it's A21. A21. And C22 is negative 1, 2 plus 2, A11. Right, so that gives you the right expression for determinant. Okay, so each of these steps, right? A11 C11 plus A12 C12 and A11 C21 plus A22 C22. Each of this is an expansion along either. So this is the expansion along the first row, expansion along the second row, expansion along the first column, and expansion along the second column. So these are the four possible Laplace expansions. Laplace expansions. Now, what is a Laplace expansion? So you have a matrix say I have a matrix that looks like this. A11, A12, not the best place to, A1n, right? A square n by n matrix. So if I, and then of course you have the other elements of the matrix. So Laplace expansion along the first row, Laplace expansion first row is basically A11 C11 plus A12 C12 A13 C13 A1n C1n. So you can do the Laplace expansion along any row or any column. So the more common name for Laplace expansion is the cofactor expansion. Okay, so cofactor expansion of determinant A. So notice that whichever row or column we expand along, we get the same expression, right? So that's what we got for the 2 by 2 matrix. Now this is, according to our next theorem, we're going to get the same expression for the cofactor expansion for any n by n matrix. So if A is an n by n matrix, then regardless of which row or column of A is chosen, the number obtained by multiplying the entries in that row or column by the corresponding cofactors and adding the resulting products is always the same. It's pretty easy to see what this theorem is saying. So if you have So for example, if I wanted to take the elements in the jth column of a matrix, right? A1j, A2j. So let's say this is the jth column, right? So this is A and J. So the Laplace expansion, the cofactor expansion on the jth column would be this: A1j times C1j plus A2j times C2j plus A all the way to A and J plus C and J. So this actually can be written as a summation, right? So you could k is equal to 1 to n A kj ckj. Or similarly, you could do a cofactor expansion along the ith row. So this would be equal to k is equal to 1 to n aik cik. Now notice that okay, so the theorem, what the theorem tells us is that whichever row or column we do this cofactor expansion along, we're going to get the same result. Right? Now the proof is of course extremely lengthy and involved, and hence understanding it is not part of the syllabus. However, I do encourage you to have a look at the proof, and so I'll give you a link to the proof on Slack, and of course we call this cofactor expansion, since it's the same whichever way you do it, we're going to call it the determinant of A, or det A. Okay, so let's calculate the cofactor the det X, right? Meaning determinant of the matrix X that we've already defined here, this matrix X, right? This matrix over here. Let's calculate the determinant of X using the cofactor expansion along the first row. Now, notice that in the first exercise, you've already calculated all the C. Notice in the previous exercise, you've already calculated the Mij and the Cij of the matrix X. So, if we do a cofactor expansion along the first row, right? So since X is a 3 by 3 matrix, we get X11 C11 plus X12 C12 plus X13 C13, right? So X11 is of course 3, C11 is 16, X12 is 1, C12 is negative 10, X13 is negative 4, C13 is 3, you got an end of 26. We could do a cofactor expansion along the first column, all right? And that will give you X11 C11 plus X12 C. The first column would actually be, so this is a typo here, X11 C11 plus X21 C21 plus X31 C31. Okay, so disregard this typo. Disregard this. Take this to be the cofactor expansion. Okay, so that's that. So notice that whichever way we do it, we still get 26, right? So because that's the determinant of X. So according to theorem 5.2, we can evaluate the determinant along any row or column we like. So the next exercise tells you to evaluate determinant via row expansion along the third row and a column expansion along the second column. And by now, since you've already calculated all theCij's, you should be able to do this easily. Okay, so what if a row or a column of a matrix involves many zeros? For example, this one, right? Notice that the second column of A, this has 3 zeros, right? how do we do a column expansion, cofactor expansion? Well, if I do a cofactor expansion on the second column, right? So you get 0 times C 21, right? Plus 1 times C 31 plus 0 times C 0 times C11, C21, 1 times, no, this is C12, sorry. The cofactor expansion is 0 times C12 plus 1 times C22 plus 0 times C32 plus 0 times C42. So you only need to know what C22 is, right? You only need C22. So what is C22? C22 is what remains after you cross out the first row, second row and the second column. So what remains is 1 0 negative 1 1 negative 2 1 2 0 1. So notice that you're now left with the 3 by 3 determinant. And to evaluate this 3 by 3 determinant, notice that this, again, the second column has 2 zeros in it, right? So you cross out the second row. You cross out the second row. Okay, so what is the what is this equal to? This is actually equal to 1 times, okay, so 0 times C21 minus 2 times C22 plus 0 times C32. So you only need to know C22. What is C22? C22 is basically this, okay, 1 negative 1 2 1, and you end up with negative 6. So choosing the right row or column can choosing right row column saves you time and energy, of course. Okay, so notice this lower triangular matrix, right? In the first row, there are 3 zeros. So I can cofactor expand along the first row. So I end up with A11 when I cross this out. So I am left with this 3 by 3 matrix, right? And then I cofactor expand along the first row again. So you cross this out, and I end up with A33, 0, A. And you end up with A33. So you know how to do this. So A11, A22, A33, A44. So in the assignment, you're supposed to prove that A for an n by n triangular matrix, A is given by upper or lower all the way to ANN, product of the diagonal elements. Okay, so let's look at the properties of the determinant. If you multiply an entire row or column for matrix A by a scalar constant, you end up with you end up multiplying the determinant by that same scalar constant. What does this mean? This means that, let's say you started with a matrix A. So let's say you know what you look at the ith row, right? So what is the ith row? AI2. So you multiply this by k, so you end up with k AI1, right? So notice that if I do a cofactor expansion, now these C's, right? These C's, they're the same in the new matrix as they are in the old matrix. Meaning the new matrix, the matrix for the ith row has been multiplied by k. So the cofactor. So if you take k out of this expansion, right, you get AI1 CI1 plus AI2 CI2 all the way to AIN CIN. But that is exactly det A. Okay, so if you multiply the jth column by k, you get the same. So the second identity is if A contains a row or column made up entirely of zeros, the determinant of A is 0. I mean, that's pretty obvious considering it's trivial to prove this, because if the ith row consists entirely of zeros, right? So you have 0 C1 plus 0. If the ith row CI1 CI2 plus 0 CIN, right? So this would be your det A. So this would be equal to 0. In fact, I should write these as CI1, CI2, CIN, right? If the ith row or column in D is the sum of the ith row or column in A and the ith row or column in V, and all the other rows in A and V are equal to the corresponding rows in D, that is A and V differ from V by one row only, then the determinant of D equals the determinant of A plus the determinant of V. What does this mean? What this basically tells you is that let's say we have a matrix A and a matrix B, all right, and they're exactly the same, right, except that the ith row in A and the ith row in V are different, right? See, they're exactly the same. A and V are exactly the same, except that this guy and this guy are different. So the determinant of D, and let's say we have a third matrix D, where the ith row is the sum of the ith rows of A and V, right? So this is the ith row of A plus the ith row of V. Now, what is the determinant of D then? If you take the cofactors of D along the ith row, so this times C1 plus AI plus 1 plus VIN 1 times C1 plus AI2 plus VI2 times C2 all the way to AIN plus VIN times CN. Now you can separate the A terms and the V terms, right, into separate summations. But this first group of terms is basically the determinant of A, and this second group of terms is determinant V. Hence, you have this to be true. However, in general, if A plus B equals D, then this is in general. this is true only in this specific case. However, in general, it is not true. So let's look at the next property. So if two rows or columns of A are interchanged, the determinant is multiplied by 1. So the proof of this, again, I'm not going to, this is going to require a different definition. This usually is a different definition. So we skip for now. We'll look at this later. However, this is a very useful formula, right? What is the theorem? The theorem tells us basically that if you switch two rows or two columns in a matrix, then the determinant is multiplied by -1. So, for example, instead, if my 2 by 2 matrix is looks like this, right? Let's call this A prime. What have I done here? I've basically switched the first two rows, right? So the determinant of A prime equals the negative of the determinant of A. Isn't that the case? A21 times A12 minus A11, A22, which is the negative of the determinant of A. Okay, part 5. Part 5 tells us that if two rows or two columns of A are equal, then determinant of A equals 0. Well, that's because, remember what part 4 tells you? Part 4 tells you that if you switch two rows or two columns, the determinant is multiplied by -1. Now, let's say the ith and the jth rows are the same. So if you switch them, determinant should be multiplied by -1. However, switching them is going to leave the determinant invariant. So determinant of A is equal to the negative determinant of A, meaning a number, some number x equals the negative of x. But this is only possible if x is 0, right? So determinant of A is 0 if two rows or two columns are identical. Now let A be, okay, part 6 of the theorem, 5.4, tells us that if we add a row or column of A multiplied by a scalar k to another row or column of A, then the determinant of A will not change. So this is an elementary row operation, right? Meaning Ri goes to Ri plus Krj. So that's not going to change the determinant. So let's add k times the jth row to the ith row, right? So the ith row then becomes this. So now notice that, so now let D be the matrix, which is exactly the same as A, except that the ith row has been replaced by Ri. Alright, so D is the same as the original matrix A, except that ith row of D is exactly this guy. Right? Now, and let B be the matrix, which is the same as A, except that the ith row has been replaced by this. Okay, so we can write that the ith row in D equals the ith row in A plus the ith row in V. Except for that, all the other rows are the same. Now notice something here. Notice that this condition here, right? This condition here, over here, is the same as the condition in part 3 of the theorem. Sum the ith row of A and the ith row of B. Ith row in D is the sum of the ith row in A and the ith row in V. So this is the same as the condition in part 3 of the theorem. So therefore, we have we may write that det D equals det A plus det V by theorem 3, part 3 of the theorem. But by part 1 of the theorem, right, what is V? The ith row of V is basically KAI1, KAI2, ... KAIN, right? But this can actually be written as KAI1, AI2, IN, right? Now, notice something here that in V, the ith row is replaced by the jth row, right? So this is KAJ1, KAJ2, KAJN. And we have two identical rows. Let's call this okay, let's look at the matrix B. Okay, let's look at the matrix B. The matrix B, the ith row looks like this: J1, KAJN, and the jth row looks like this: J1. Now let V prime be the matrix such that the ith row is this. This is the ith row, and the jth row is this. Right? I know that the determinant of V prime is 0 because the ith row and the jth row, they're the same. But the determinant of V is K times the determinant of V prime. This is 0. So since the determinant of V prime is 0, determinant of V is 0. So determinant of D is the determinant of A. Right? But so then the determinant is unchanged. So what we have proven, therefore, is that the determinant is unchanged by this operation. Ri goes to Ri plus K Rj. Okay, so the next part, which is part 7, it tells us that the determinant of Ka is K to the n times the determinant of A. So if you multiply a scalar, right, by the matrix, it's the same as multiplying the determinant by K to the n. So this is pretty easy to see. You have each row multiplied by K, K12, KA1N, KAN1, KAN2, KANN. So you take the determinant. So if one row is multiplied by K, right, if one row is multiplied by k by part 1, the determinant is multiplied by k to the 1, right? So if n rows are multiplied by k, then determinant is multiplied by k to the n. So that's exactly what the theorem is saying. And the last part, determinant of AT equals determinant of A. So the cofactor expansion along the ith row of A is the same as the cofactor expansion along the ith column of AT, because what does transposition do? Transposition switches the rows and the columns. So determinant of A equals determinant of AT. So from the previous statements, one thing is made clear of the determinants of elementary matrices. So if E results from the multiplying any row by k, then determinant of E equals k, because let's say we have an elementary matrix that looks like this, right? Multiply the second row by k, so that tells you the determinant of E is k. So the determinant of EA is of course k times determinant of A, which is the same as determinant of E times the determinant of A. Now if E results from interchanging two rows, then determinant of E is -1, because you just switch signs, and therefore determinant of EA is the negative of the determinant of A, which is the determinant of E times the determinant of A. And if E results from adding a multiple of one row to another, then determinant of E is 1, and determinant of E is equal to determinant of A, because adding a multiple of one row to another, as we saw in the previous theorem, does not change determinant. So this is equal to determinant of E times the determinant of A. So no matter what happens, this is the case. Determinant of E times determinant of A is equal to determinant of EA. And of course, if we can extend that to an arbitrary number of elementary matrices, E1, E2, all the way to A equals determinant of E1, determinant of E2, determinant of EK times determinant of A. Now this theorem will actually be used to prove very important statements about determinants. The first thing we do is we look at the invertibility of a matrix and its determinant. So if A is a square matrix, and if determinant of A is 0, then A is invertible. Conversely, if A is invertible, if A is a square matrix and determinant of A is 0, then if A is invertible and determinant of A is 0, if A is invertible, then determinant of A is not equal to 0. And if determinant of A is not equal to 0, then A is invertible. Okay, so that's what this theorem says. So this is what you would call an equivalence relationship. Okay, so what is the proof of this? So from our equivalent theorems about matrices, we know that this is from the previous chapter. We know that A is invertible if and only if the RREF of A is the identity matrix. This we know. And we also know that A is expressible as a product of elementary matrices from the same theorem. So let R be the RREF of A. Then of course R equals this. Let's say you need k elementary row operations for this, right? Now so you have k elementary matrices. So then determinant of R equals determinant of ek times determinant of ek minus 1 all the way to determinant of E1 times the determinant of A. Now, A is invertible if and only if the RREF of A is equal to I. So which means the determinant of R equals 1, which is not equal to 0. Okay, so we've proven one side of the theorem, meaning if determinant of A, if A is invertible, then determinant of A is not equal to 0. Because these determinants, these are non-zero, right? So if this is non-zero, if these are non-zero, then determinant of A is non-zero. Now we prove the converse, the reverse statement, right? Of course, we start with stating the determinant of A is not equal to 0, but that means that the determinant of R is not equal to 0, right? But a square matrix in its reduced to echelon form is either the identity matrix or it has at least one row of zeros at the bottom, right? There are only two possibilities. Only two possibilities, right? Now, since determinant, try to prove this because this might be on the final exam. So, since determinant of R is not equal to 0, so there is no row of zeros at the bottom. So which means that R must be equal to the identity matrix. Hence, since R is equal to the identity matrix, by the equivalence statements of our theorems, we know that reduced R is equal to since R is equal to the identity matrix, we know that A is invertible from the equivalence statements of what matrices. So we've proven this both ways. Okay, so now what we're going to do, so we're going to prove a lemma. A lemma is basically a helping theorem. Meaning a lemma is a theorem that is used to prove other theorems. So the lemma tells you this, is that if A is not invertible, then AB is not invertible. Right? Remember, we had AB inverse equals B inverse A inverse. So if A is not invertible, if I can't find the inverse of A, right? Then I can't. Then I cannot safely say that this is equal to B inverse A inverse. Then I cannot find the inverse of this. So what is the proof of this statement? Well, let A be a non-invertible, right? And let R be the RREF of A, the reduced to echelon form of A. Then R must contain a row of zeros at the bottom, right? That is a given. So the determinant of RB, okay, this determinant is equal to determinant of the products of the determinants of the elementary matrices that are used to bring A into its reduced to echelon form times the determinant of AB. We know this from theorem. We know this from where? We know this from theorem 5.5. We know this from theorem 5.5. Okay, but since R, it has a row of zeros at the bottom, so must RB. So if you have a row of if this is your R and has a row of zeros at the bottom, then any R times any matrix must also have a row of zeros at the bottom, because the nth row, right, of R multiplied by the columns of V, right, is going to give you the nth row of RB. So RV must have a row of zeros at the bottom. So determinant of RV is 0. Now determinant of RV is 0. So this, and I know that the determinants of these elementary these are not 0, right? So these guys are not 0. Not 0. So determinant of AB must be 0. Right? And hence AB is not invertible, right? So this should say that hence AB is not invertible. That's what we want to prove. Does not have an inverse, right? So now what we're going to do is we're going to prove a very important theorem about determinants, which is that if A and B are two n by n matrices, then the determinant of AB is the determinant of A times the determinant of B. How do you prove this? Well, let's say A is not invertible. Right? First case, let's say A is not invertible. Then determinant of A is 0. And then of course AB is not invertible by lemma 5.7, and hence determinant of AB is 0. So this is 0 and this is 0. So LHS equals RHS, not a problem. But then if A is invertible, then A is expressible as a product of elementary matrices via our equivalent theorems about matrices, right? So A equals E1, E2 all the way to ER, right? Product of elementary matrices. So the determinant of A is the product of the determinant of these things. So by theorem 5.5, we have determinant of AB equals determinant of E1, E2 all the way to ER times V, which is determinant of E1 times determinant of E2, or of ER times determinant of V, which is the same as the product of these guys, right? E1 dot ER times determinant of V, which is determinant of A times determinant of V as required, right? So we've proven this theorem. So now, since we've proven that A is invertible if determinant of A is not equal to 0, we can add this to the equivalent statements about matrices that we have. Notice the last statement, determinant of A Notice the last statement, determinant of A is not equal to 0. Okay, so that's that. So our statements are A is invertible, AX equals 0 has only the trivial solution, the RREF of A is IN, right? And then A can be expressed as a product of elementary matrices. AX is equal to V is consistent for every n by 1 matrix B. AX equals V has exactly one solution for every n by 1 matrix B, and determinant of A is not equal to 0. Okay, so let's look at the so now we'll look at the inversion algorithm. Right? We look at a new way to prove we will prove a new way to invert a matrix. Okay, so if A, let's define what adjugate matrix is. Okay, so if A is an n by n square matrix, right, and then you replace the elements of A by their cofactors, right, then you get a cofactor matrix. Then you get the cofactor matrix corresponding to A. It's called the matrix of cofactors. And then when you transpose that, you get a matrix that's called the adjugate of A, right? ADJ A. So the transpose of the cofactor matrix is ADJ A, adjugate A. Okay, so theorem 511 tells us that the inverse of A is 1 over determinant of A times the adjugate of A. So let's prove this. So let C be the cofactor matrix of A, and let I be an integer between 1 and n inclusive. So A times the adjugate of A, II, the II element, you mean the diagonal element of this guy, diagonal element of this guy. So this is equal to AIK times adjugate of AKI, right? But adjugate of A is the transpose of the cofactor matrix, right? So CTKI is CIK. This is equal to det A, right? Because this last summation, right, is basically cofactor expansion along the ith row, right? So now let J be between 1 and n, right, such that I is not equal to J, and let A prime be the matrix that is the same as A, except for the jth row of A prime has been replaced by the ith row. Then of course, now because the ith and the jth row are the same, det A prime equals 0. And therefore, A times the adjugate of A, the ij element of that, equals AIK times the adjugate of AKJ, which is equal to AIK times CTKJ. It's equal to AIK CJK. Just switch the K and J. KJ becomes JK. But AIK is the same. Remember that ith row of A and ith row of A prime are the same. So this is A prime IK. And CJK is the same as C prime JK. It's the same. But for C prime, the cofactor, remember C prime is the cofactor. Matrix of A prime. So this is equal to det A prime, which is 0. This is the Laplace expansion along the ith row. Okay, so Laplace expansion or cofactor expansion along the ith row. So we can summarize what we've seen as follows. The ij element of A times the adjugate of A is equal to det A if I is equal to J, and this is equal to 0 if I is not equal to J. So all of this can be written as A times adjugate of A equals det A times In, or A inverse is 1 over det A times the adjugate of A. So that's easy to see. So do the exercise. Do the exercise. Do the exercise. Okay, so now we have a new way to solve simultaneous equations. It's called Cramer's rule. So you have a set of simultaneous equations, AX equals V, n linear equations in n unknowns, right? Such that and you have the determinant of A is not equal to 0, right? So the solution is, of course, x1 equals determinant of A1 over det A, x2 is equal to determinant of A2 by determinant of A, xi is determinant of I with det A, xn is determinant of an by det A. So determinant of an is what you get when you replace the ith. Okay, determinant of ai is what you get when you replace the ith row of A by the right hand side, which is V. So just for practice, okay, so the proof of Cramer's rule is from pages 124 and 125 of Howard Anton. I'll not repeat it here. And for practice, you can solve these simultaneous equations using Cramer's rule, and the solutions are given. Okay, now let's look at a geometric interpretation of what of what determinants are. So let A and V be two vectors in R3, right? So the cross product of A and V is defined as A cross V is A2V3 minus A3V2, A3V1 minus A1V3, A1V2 minus A2V1. Now this cross product is also a vector. Right, this is also known as a vector product. Okay, so the cross product has the following properties. A cross V equals negative V cross A. It's called anti-commutativity. A cross V is orthogonal or perpendicular to both A and V. A cross B is equal to the modulus of A times the modulus of B times sine theta times n hat. Now what is theta and what is n hat? Let's pay attention to this diagram. Theta is the angle between A and V. Okay? And n hat is the vector that you get, that your thumb points towards. If you curl four of your fingers towards your palm, if your four fingers are pointing in the direction of A, and if you curl them towards your palm, which is in the direction of V, then your thumb will be pointing in the direction of A cross V. Right? This is of course if you're doing it with your right hand. Right? So think of a clockwise screw. Right? If you turn it anti-clockwise, as in from A to V, you're going anti-clockwise, the screw goes up, right, in the direction of n hat. Okay, that's that. And of course, A cross V is 0 if A and V are parallel or they're anti-parallel. And of course, A cross A is 0. The area of a parallelogram with adjacent sides defined by the vectors A and V is given by the modulus of A cross V. Right? If the parallelogram is defined by A and V, and this side is of course A, and this side is of course V, the area is A cross V. Right, so that's that. And of course, let's introduce a third vector C. Right, so A dot V cross C is known as the triple scalar product of A, V, and C. And you can show that this triple scalar product is equal to this determinant. Right? A1, A2, A3, V1, V2, V3, C1, C2, C3. Now, what is this geometrically? Geometrically, this gives you a figure that is known as a parallelepiped, right? Or parallelepiped, whichever way you would like to pronounce it. The property of the parallelepiped is that this opposite faces, right? They're the same parallelogram, meaning this face, and this face, they're the same parallelogram, and this face is the same parallelogram. A cube is a specific example of a parallelepiped or parallelepiped. So this determinant, it gives you the volume of the parallelepiped with a sign, right? Meaning you'll get the volume and you'll get a sign along with it. So if you take the modulus of this determinant, you get the volume of the parallelepiped. Okay, so that's okay. So the next exercise basically tells you to find the area, the total surface area of the parallelepiped. Okay, so that's that for this lecture. I'll fix the typos and re-upload the lecture notes on Google Drive and on VUX. Okay, thank you very much for listening.